All right, today we're going to talk about the greenhouse effect. So to begin, let's answer this question. Why do cars get so hot on sunny days? I'm sure you've experienced this before. Let's say you leave your car out in the parking lot at the mall, you go in for a few hours, and you come out on a sunny day. You open the door, and it seems like the inside of your car is an oven. Right? I'm sure we've all experienced this. That's the reason why you can't leave small children and pets inside of your car. But why does this happen? Well, the answer is pretty straightforward. Short-wave radiation, such as visible light, passes through the window and is absorbed by the car's interior, say the seats or the cloth or the plastic. This radiation is emitted as a longer wavelength, such as infrared, and cannot escape. The best way to prevent this is to simply keep the light from being absorbed in the first place. So I included this picture. As you can see, if you can prevent the light from hitting the inside of your car and reflect it with some reflective material, that's ideal. So what happens is solar radiation comes in, passes straight through the window, as we know. It bounces around the inside of the car, and some of it can escape, right? But most of it just gets trapped inside the car, and it heats it up. So it's a pretty straightforward process, and greenhouses work the same way, hence the name, right? The greenhouse effect takes advantage of this phenomenon in which shortwave radiation comes in, it gets absorbed by things inside the greenhouse, plants, and the light that's emitted, the infrared radiation, gets trapped. Okay, some of the long waves escape into the atmosphere, but a lot of the energy is trapped inside of the greenhouse, and we can take advantage of this living in a cold climate. In winter, we can keep plants alive, like you see here, even when the outside temperature is quite cold. Okay, let's relate this to the Earth's atmosphere. So if the Earth were the size of an apple, the atmosphere would be as thick as the skin of the apple. Okay, a lot of people don't realize exactly how thin the atmosphere really is. I think it's because we see it in diagrams like this, where we overemphasize the thickness of the atmosphere, when in reality it's just a very thin sliver. It's not very thick at all. The atmosphere is comprised mostly of nitrogen. About 80% of the atmosphere is N2. About 19% is about the composition of O2. And then, surprisingly, the third biggest is argon. And then very trace amounts of everything else, including carbon dioxide. Okay. Now let's watch this video that helps explain the greenhouse effect in relation to the entire globe. Okay, it's not a very long video, I'll just play it here.
The Earth and the Moon are basically the same distance from the Sun, yet temperatures on the Moon average an unlivable negative 18 degrees Celsius. And even deadlier, they range from negative 170 Celsius during lunar night to 100 Celsius at lunar noon, regularly exceeding both the coldest and hottest temperatures ever recorded on Earth. And while the days and nights on the Moon are about 14 times longer than those on Earth, our planet's relatively fast rotation isn't what spares us from those loony temperatures. What protects us is our atmosphere. By day, it serves as a shield, blocking out the most harmful and energetic of the sun's rays and about 1/3 of the less intense but visible light. At the same time, it traps the infrared radiation, aka heat, radiating out from Earth's sun-warmed surface, keeping us from freezing solid at night. In order for our atmosphere to absorb any kind of radiation, it needs to have some electrically charged particles for passing electromagnetic waves to push around. And most of our atmosphere is made up of gas molecules that don't have an electric charge. They all have a balanced number of positive protons and negative electrons. But some molecules hold most of their negatively charged electrons closer to one side, lending them a lopsidedness that can jiggle back and forth to absorb the energy of incoming infrared rays. For example, water, ozone, and nitrous oxide are all electrically lopsided, so they all absorb infrared radiation. Then there are gases like carbon dioxide and methane. On paper, neither molecule looks lopsided, so it doesn't seem like they should be able to absorb any radiating heat. But in reality, gas molecules aren't motionless. They crash into each other billions of times per second, knocking each other in different directions and also into different modes of rotation and vibration. And it turns out that both carbon dioxide and methane spend most of their time shaking it in electrically lopsided ways, allowing them to absorb infrared rays and help insulate the Earth. Even though many different kinds of molecules can absorb infrared radiation, the vast majority of our atmosphere can't, because it's made of nitrogen and oxygen, which don't get lopsided even when they are vibrating. They're too symmetric. Nevertheless, the lopsided 1% are such good infrared absorbers that they manage to intercept about 90% of Earth's outgoing heat. Each captured ray gets pinged around the atmosphere, and most end up returning to the surface at least once before escaping to space. We don't need to visit the moon during frigid lunar night to know just how important the game of radiation pinball is for Earth. Ice records from our own coldest climate show that small natural variations in atmospheric carbon dioxide produce relatively big changes in temperature. They also show that, compared to the last 800,000 years, the game today is much, much harder. Thanks so much to the great team over at Kurzgesagt for doing the animations in this video. It's been a lot of fun working with them. And if you liked what you saw, you can go to the link here or in the video description to check out their channel, where they cover everything from neutron stars to fracking to the Islamic State. Thanks again, Kurzgesagt. And thanks as well to everyone who has supported us on Subbable.com, which has now merged with Patreon.com. You make Minute Earth possible.
Okay, so I like that video a lot. It has very good animations. The greenhouse effect is not an unnatural phenomenon. It is very much natural, and it's something that's crucial to the Earth in keeping us relatively stable in terms of temperature. If we didn't have an atmosphere, we would be somewhat similar to the moon in that it is extremely cold. But likewise, if our atmosphere is too thick and it produces a greenhouse effect that is too strong, we have the opposite problem, much like what Venus experiences, where temperatures can get up to 800 degrees Fahrenheit. Okay? So, the key to the game is to make sure that everything is about the same. All right? So this slide, why I included this one is for a specific reason. If you've ever heard this phrase before, or this saying, you may understand why. So it says, when you can't see the forest for the trees. Now, what does that mean? That means, essentially, don't get caught up in the details, look at the big picture instead. Okay, so you'll hear a lot of people try to discredit climate change, global warming, by saying that, right, small variations in the weather prove that it's not happening, that global warming isn't occurring. Now let's look at this next video here and see why that might be an incorrect assumption to make. This is a very quick video.
A common mistake when interpreting statistics is to look at them from too short a distance. This can make everything unclear and confusing. So forget the details and take a step back. You're looking at the dog when you should be concentrating on the owner. As you can see, the dog is all over the place, leaping and bouncing, sometimes upwards, sometimes downwards. But where do you think it'll be in 10 seconds' time? Around here, right? But at this moment, the dog is on its way downwards, so why do you think it'll find itself up there? It's because you've noticed the owner. The owner is the trend, and it's he who determines where they both will be in a while as a bit longer than a couple of dog bounds. He could change direction. There's a lot we don't know about this guy. but everything we do know indicates he's heading in that direction. The owner is the long-term trend, the dog is the variation around this trend. Or, the owner is the climate, the dog is the weather.
Teddy?
Okay, so like the video said, we have to pay attention to the difference between variation and trend. So I'm going to draw a quick picture up here. It's sort of like the stock market. If you have a stock that sort of does crazy things like this, but you can see that it has an overall trend, right? You could draw a straight line right through it and predict in the future generally where it's going to be. You wouldn't predict that it would be down here all of a sudden. There's no reason to predict that. So just keep that in mind. The difference between variation and trend is very similar to what we see with weather and climate. Okay, so the greenhouse effect keeps the Earth's temperature relatively stable. That is the whole point of it. Gases that contribute to the greenhouse effect, called greenhouse gases, the two that are the most notorious are carbon dioxide and methane, both of which are on the rise. The Earth does go through natural cycles of hot and cold periods, but never as quickly and dramatically as we've seen recently. Okay, I'm going to click on this and go to this website, which I think is really good, just to show you some of these trends. Let's wait for it to load. Okay, so this is going to show carbon dioxide levels from more recent and historical data. Okay, so what we have here is on the x-axis back 1,000 years all the way up to present time. Let's look at the last, say, century or so. Let's zoom in on this part. Okay. And let's overlay this with temperature, shall we? There it is. As you can see here, over the last century or so, we've seen a drastic increase in carbon dioxide levels. Okay. That's pretty alarming. And you can see that the temperature goes up as well. You can zoom in on this as well. Excuse me, if you want to. Look at this yourself. You can see that temperature and carbon dioxide levels are extremely highly correlated, right? They go up and down together. Let's reset this zoom back. And you can see that there is an upward trend here. You wouldn't predict that it would end up down here by the year 2050, right? Down here. You would predict that it would continue to rise. There's no reason to think that it would do otherwise. Okay, so there's more information down here, and there's actually a video that I've included that will talk about more of this. So human activity, such as burning fossil fuels, as you can see here, from cars and refineries, are the largest contributors to greenhouse gas emissions. But where does all this data come from? This is a quick video that I think will help clear that up. How do we know what the composition of the atmosphere was in the past? Nowadays, it's pretty simple. We have satellites that can do this for us. But to look in the past, there's a very specific thing that climatologists do.
It's a busy, freezing cold day inside the National Ice Core Lab in Denver, Colorado.
Gonna cut gas samples out of this core?
Scientists from Maine to California here to cut pieces of precious Antarctic glacier ice to take back to their labs for study.
We started the Ice Core project in 2005.
With support from the National Science Foundation, For a project called the West Antarctic Ice Sheet, or WAIS Divide, lab manager Mark Twickler and a team of scientists, engineers, and support personnel traveled to the bottom of the world to drill out and bring back these ice cores. The goal of the project? To collect and study perfectly preserved records of the distant past.
The unique things about polar glaciers is each year that it snows there, the snow never melts. So you get 1 year of snow on top of the next year of snow. It compresses, so everything that fell out of the atmosphere, dust, salt from the ocean, volcanic ash, is preserved in that ice core.
This particular ice sheet is more than 70,000 years old. The team drilled down more than 2 miles into it to retrieve these cores, which were then flown to the U.S. and stored in a giant 40 below zero freezer here at the Ice Core Lab.
Inside this freezer contains more than 10 miles of ice cores collected from around the world.
Twickler says the ice core's layers are like tree rings, each layer representing a year of weather and snow.
We can tell what the temperatures were. We can tell how rough the oceans were around Antarctica. We can tell how dusty Australia was.
Scientists are keen to study the bubbles trapped in the cores, each a tiny pocket of air frozen in time.
We can measure a variety of gases that were in the atmosphere at the time the bubbles were formed.
Other scientists want to know how ice sheets melt over time.
We don't necessarily have a really good handle on how the ice sheet as a whole will respond in a case of changing climate.
Twickler says this icy blast from the past is helping researchers better understand the mechanics of climate change, and that in turn will help them make better predictions as to what a changing climate may mean for our future. For Science Nation, I'm Miles O'Brien.
Okay, so I really like that video. Let's move on from this. Okay, because it shows generally how scientists can predict future weather patterns, or climate patterns in this case, based on what was happening in the past. Okay, let's move on to this slide, clearing up some terminology. This is important because as students of science, we need to improve our scientific literacy and make sure that we're all talking about the same thing when we discuss these topics. So I really wanted to include this because I see this get mixed up a lot in the news. The greenhouse effect, which is what we've been studying, right, is the cause. The greenhouse effect with the incoming radiation, outgoing radiation, causing warming due to the way that light interacts with matter. That leads to global warming, which is the change. This doesn't always occur, but it has been recently. We can see that an increased greenhouse effect leads to the average temperature of the globe rising, right? Even just fractions of a degree Celsius. And global warming, the result of that is then the effect, the ultimate effect of climate change. Okay, and this is the part where there is some controversy as to what exactly this entails. What are we going to expect in the future in terms of climate change? How are climates going to change? What will be the ultimate result of these things? So what I would like you to understand is that the greenhouse effect can lead to global warming, and global warming can lead to climate change. It's as simple as that. These three terms are not synonymous. They are distinct parts of this process. Okay, and lastly, we need to talk about climate change, right? Climate change is a hot topic recently, even more so now with the new president and some policies that may be changing. Okay, climatologists are not certain what the long-term effects of global warming will be. However, some are already visible I'll go to this link in just a second. For more information, visit this website. I have a link to it on Canvas. But let's look at some of these pictures because I think they're, excuse me, very interesting. Okay, and we'll end here with these images. Give it a second to load. All right, so what we can see here is 2 Kenyan lakes, and the dates are down here. 2013, 2020 is on the left and the right side, respectively. Okay, you can see how drastically some of these environments have changed in not really that long of time. Here's a stalled landslide threatens tsunami in Alaskan territory here. Isn't that interesting? You can see that glacier is significantly smaller in the after picture. Flooding in northeast China, okay, as you can see, there's a clear difference here. This would be the before, and this is the after. Okay, let's look at one more here. The invasion of the water hyacinths across Velasquillo Reservoir in Mexico. Okay, you can clearly see that there's a huge difference there as well. You can continue to look through these as you want, but it's pretty surprising. Look at that glacier and how it disappears in a matter of about 34 years here. That's what it says. So go ahead and check those out. That's all I have for this topic. You guys will be doing some more research, and as always, just let me know if you have any questions.